All right. Okay. Welcome back, guys. We are going to go through another Kaggle mini courses. We are just continuing from the last session. I think it's machine learning part six, I believe. Now it's going to be the continuation of that. So we are going to go through this it's called machine learning competitions, taken again from the Kaggle. Okay. Um, so what I'm gonna do here, just gonna put the GPU on, just make sure it's just a little bit faster, but I don't think it's gonna make a difference because it's just the data set for this particular exercise is just not not too big, I think. Right. The one that is gonna make a really difference if you trying to compute a lot of uh, big data set, right? So let's see how this works. I'm just going to minimize this so it's a bit cleaner. So again, introduction. Machine learning competition are a great way to improve your data science skills and measure your progress. In this exercise, you will create and submit prediction for a Kaggle competition. Ooh, cool. Let's see how this will go. Otherwise, we're gonna break it into chunks, right? So you can then improve your model by adding features. So you want, remember when we talk about model, what it means is the algorithm, the formula, the mathematical formula, right? Mathematical function. That's what model is basically, right? It's just in machine learning or even in deep learning area, it's just a complicated um, um, mathematical functions. You heard the expression E equals to mc squared. That's another mathematical function. Another mathematical function is the Pythagoras theorem is z squared equals to x squared plus y squared, right? So, and then of course the exponential function y equals to e to the power of, say, 2x, for example. Yeah, so in a deep learning machine learning model, the parameters, or they call it, I think, the hyperparameters, could be in a form, I mean, could be hundreds, could be thousands, could be even 10,000, could be 100,000, it could be millions. That's why it's make it very complicated. So you can make it complicated by adding features. So the more features you have, right? Uh, right. The more features you have, then in general the formula, the model is gonna get more complicated. Now the great thing about machine learning as compared to deep learning, or deep learning as compared to machine learning, is in deep learning the adding of the features is done kind of automatically instead of manual. In data science or in machine learning world, this adding features is more like a skill that's it owned by the um, domain expert in that particular area. So, for example, if you want to predict the number of housing in this example, then you want to consult, for example, people who already has experience about 20 years in the housing industry, who does a lot of transactions in the realtor world. So he or she knows what kind of features that are important that has to be incorporated in a machine learning model, right? But if you have a deep learning, going to the deep learning, which is a subset of a machine learning, then you might not, you still might want to consult the domain expert in that particular area, but it's kind of, it's nice to have to, but it's not necessary because the deep learning model will kind of the one who is the ones kind of picking up. So the trade-off is in the deep learning model, you have to need to have a lot of data instead of in the data in a quantity of hundreds or even 1,000s. You'll have data in a quantity of 1 million or even 100 million, 10 millions, or even 1 billion. So because of that, uh, tons of data, the algorithm in a deep learning model can kind of extract the correlation or the relationship between features with regards to the output. So in that sense, the deep learning model, it's kind of automating, right? But you need to feed them a lot of data. So that's like kind of the trade-off uh, in terms of you don't need a person to tell you what features are important, but you need in exchange of that you need tons of data, you know. So it's like saying in a machine learning model you need the expertise, the domain expertise, right? You need the person to tell you because you only have kind of have a limited data, right? Data in really data set, right? So the algorithm of in the machine learning or in the data science, you cannot like predict or extract any valuable relationship or any valuable uh, between parameters, which which parameters are related, which parameters are not related, because at the first place you only have a few data. So you need somebody, a human being in this case, in exchange for this data, right? To tell you what features are important. Or in the real estate, for example, oh, it could be the number of bedroom, how many square feet do you have in the first floor? Do you have a swimming pool at the backyard? How big is your like your living room? How big is your kitchen? Like all that features, like the nitty-gritty stuff, you need somebody to tell you in exchange only because you only have a small data set. That's kind of makes sense because when somebody kind of like tell you come into the scene, the domain expertise, that people actually incorporates a lot of how do you say it, data in his or her head, right? Because the person, the domain expert, has been working for so many years in that particular field, so he has tons of data in his head, right? So in his head is, you imagine like his or her head is like a computer, so he knows the head, I mean, sorry, no, the data are already on his brain. So he kind of extract because he's seen a lot of tons of, again, like millions of, probably like, not probably millions, but probably like in order of hundreds, 10,000, you know, instead of a layman person, you never seen any, have that experience, probably only like in the order of 1 or 10 kind of experience. But if you bring in the domain expertise, on his head is kind of there's like 10,000 experiences, the same like on in that particular field. So he gathers kind of a lot of data on his head, right? But in an order of 10,000, of course, not in the magnitude of like 1 billion, because human head is probably going to explode because of that. So in his head, he can like sort of like has a machine learning model on his head or deep learning model, and that's why actually deep learning is basically has the inspiration from the working knowledge of our brain, which is the firing of the neurons, the interconnected of each of the neurons, and so on, right? So on his or her brain is sort of like extracting all of these features based on his hundreds or even thousands of data set available on his head because of his experience. And then he will tell you, okay, Danny or Tom or Jim or Susan, these are the features that are important. A, B, C, D, E. So if you, I hope it makes sense, you know, that's kind of like the trade-off. Yeah, just remember, if you have small data set, then you need an expert to tell you, right? Because a small data set plus an expert is kind of make it a big data set, right? Because the expert content has a lot of knowledge on his head and can extract what features are important, right? Because remember, his head, you can think of his head is like a deep learning algorithm on his head, like specifically on his head, like literally like a subset of his brain has a kind of deep learning model embedded on his brain that can extract valuable information, which is actually much more effective than the deep learning model in a computer science sense, right? Because in a computer science sense, you need to get like 1 million or 1 billion data to extract valuable information. But human head, you can give it like 100 or even like 1,000 features, and then our brain can already like get the patterns right from the data. Okay, this is important, this is important. But computer doesn't work like that. Computer is kind of like I don't know, um, more stupid kind of than us, so it needs tons of information, right? but it's kind of the same. So if you have small data, how do you extract the information? Then you get a human expert to chime in, right? But if you have because um, there's already deep learning model embedded in this set, right? But if you have used deep learning model, then you already have a big amount of data set, right? And you don't need uh, the domain expert. So um, okay, okay, so here the steps in this notebook are first you want to build a random forest model. We talked about this our last session with all of your data, and then read in the test data, which doesn't include values for the target. Predict home values in the test data with your random forest model. Submit those predictions to the competition and see your score. Optionally, come back to see if you can improve your model by adding features or changing your model. Then you can resubmit to see how that stacks up on the competition leaderboard. Okay, so recap. Here's the code you've written so far. Okay, so again we import the pandas. Pandas is like a Excel spreadsheet for data, right? For data science. We're gonna import the random forest regressor from sklearn. Um, to see how accurate it is, we're gonna import algorithm called mean absolute error, and then to the model selection is basically to uh, validate your model after you train it, right? So in order to do that, you kind of have um, to divide the data into two categories. One is for training, one is for test, right? Um, and then you are importing another algorithm called decision tree regressor. I'm not sure what's the difference. Um, I think we can learn more about this later. This is, I think, just a learning tools that they use to check whether your answer is correct or not. Okay, so right now we're gonna import the let's see the data from this guy input train.csv. Um, yeah, I don't think it's here. This is the housing example. Yeah, you can see it from here. I think it's different. Yeah, it's not here. Anyway, um, okay. Anyway, so I'm just gonna close this just to make it nicer. Um, okay, so we're gonna um, put it in a um, nice kind of frame using Panda, right? Um, so you run this code, uh, and then you create target object and call it Y. Okay, home data dot sell price. Um, why the sell price? Because that's the output um, that you want to optimize the data of, right? Because you want to um, get the kind of the predict the sell price of the house. We're trying to predict the sell price, right, of the house, so we can sell it or buy it accordingly, right? That is the objective of the algorithm, to predict the sell price of the house. Given uh, the house data, then you will know like, okay, this house we can sell it for 100,000. This house we can sell it for like 200,000. So these are the features that are given. This is where I think where we need to consult to our domain expert, right? What are the features has to be incorporated here? But in this case, we put the lot area. the year it was built, whether it was like year 1999 or year 2001 or 2003. Um, the first floor square feet, second floor square footage, whether he has I think full bath or not. Um, you have bathroom above ground or not, I think, and then the total room above ground, right? I think it's in the square footage. Okay, and all of this we call it X because this is the kind of the input, right? The input. You want you have the X, you have the output, right? So given the features, which is the lot area, your year build, first cross square foot footage, and blah blah blah, you want to know how much is the house price, right? So we call that X. Um, and we next we are going to split uh, the into training and validation. So we call this algorithm train test split. We put the X inside, right? Um, and then the Y, and then we have to put a random state equals to 1. You can put it 0 or I think 2 or 3, I think. This to make it reproducible, right? Um, why do you put the X and the Y? Because again, you are going to train, right? You're going to train the model, right? But before you train the model, you need to split the data into two category for training purpose and for validating purpose, right? And all the data is in the X and the Y, right? So you want to split those X and the Y into two category, basically. That's why we need to put the X and the Y as a parameters here. And then as the output, you have the train X, which is the data of X, yeah, right, for training purpose. And then the validation X, which is the data for validation after you train it for X, right? The same thing for the Y. There's a train Y, which is the data for the output that for training purpose, which is the home sale price, and then the data for validation purpose of Y, right? Um, and then we want to specify the model. So we are calling it using decision tree regressor. Yeah. So this is the kind of the algorithm we are using, right? And we want to make it reproducible. So random state one, and then we are training it right now. Fitting is the same as training. So every time you hear the word fit, it's just mean you are training the model because fit means basically means you are literally trying to um, see what uh, hyperparameters that can fit for the model. You know, like if you want to build, for example, algorithm of y equals to ax plus bc, right? So you want to know what is the a, what is the b, whether it's going to be y equals to 5x plus 3z or y equals to 10x plus 100z or y equals to x plus 5c. So those are the a and the b is kind of the variable that you're looking for um, when you are um, uh, running this dot fit. This is what uh, literally what that's the variable what kind of variable it's trying to look for. So this process is called fitting or called training because you're putting all of the input parameters for the training purpose. So that's why the parameters here is the training S, and you're also putting the what should be the output, right? Uh, for that, right? So if you're like, imagine if you have an algorithm of y equals to ax plus, yeah, y equals to ax, right? So you put all the training for the x, or right, the data for the x, and then you put all of the data for the y, and then you're gonna find the a, right? That's what this model is doing. So after you got the model, you want to validate, right? So you call it again because that model is now called Iowa model, and then you call it dot predict, right? And then what do you have to put inside? Well, you need in order to predict, you need to put the data for the validation, right? Because remember, you want to validate, and you want to put the X, of course, not the Y, right? Because that's the input, right? So, and then you got the prediction inside this variable, right? And then you want to know what's the error. So you call the algorithm called mean absolute error, and then the parameter is the the validation predictions, and you want to compare that with the validation of Y. So this is the predicted output that you get from the model, right? You get from the model, and this is the real output, the validation Y, right? The validation Y is coming um, from this, right? The train test split, right? So we got two real output, right? We one is for um, sorry, one for training, one for validation, right? So you want to compare the if you want to see how good your model, um, then you want to compare it to the validation. So you compare it to the real validation of Y, and then you compare it to the one that you got the output from the prediction, right? Right. So that's why it's from here. Don't worry about it. This is kind of like probably like a bit confusing for the first time, even for me, but you'll get used to this kind of like a idea of training versus validation, right? But the main idea is you cannot just trust whatever the result of your training. You need to validate it, right, before you kind of deploy that algorithm to the real world, right? Or you release that to the public, for example, for people to use it, right? Because who knows, might be your algorithm, your model after the training is not correct, right? So you kind of like test it. This is like the quality control process, right? So to speak. That's the way I see it. Um, and then you're using the best value for max leaf nodes. Okay, so this is I think trying to use an algorithm that optimize because this is kind of a decision using a decision tree algorithm, and decision tree, like there's a head and there's a leaf, there's a leaf, right? So, and decision tree comes with many different kind of forms. You can choose like 100 leaves, you can choose 20 leaf, you can choose 30 leaf, um, and we do not know which one is the optimized kind of decision tree algorithm for our specific problem. So this algorithm, decision tree regressor is called, is taken from, okay, so where is it? Yeah. Um, so so decision tree regressor, so you just specify the maximum leaf nodes is 100. It was, how do you get this? I think we got this. I forgot already. How do you get this? But I think we kind of run like several iteration. Uh, which one give you the lowest kind of um, um, validation of the mean squared error, mean absolute error, sorry, right? So for example, you run the Iowa model for maximum leaf node equals to 20, and then you compute this, and then you run again for maximum um, um, the Iowa model for let's say I don't know, maximum leaf for 50, and then you run this thing again, and then you run it again for maximum lift for 100, and then you kind of compare it, which one has the lowest, right? Because you want to have the lowest kind of error, right? After you compare between your prediction and the actual output, right? So yeah, so so you kind of, so here you train it again, okay, and then you predict again, okay, and then you got the mean absolute error, okay, okay, so okay, and then over here is you define the model, set random set to one, uh, so you're using this one, this guy, this is a new algorithm, you train it, okay, so this is a different algorithm, okay, we'll just run this, let's see what happens. It's gonna be more clear. Okay, so this is the validation mean absolute error if you don't specify the maximum leaf node. So this is the printout after from this guy, right? So you got 29,000 kind of error, yeah. But if you specify the maximum leaf nodes equals to 100, so this algorithm's kind of like finding like the best kind um, of number of nodes, leaf nodes, right? And then so the error kind of reduced by like 2000 points, right? So it's to 27,000. But if you choose this one, the random forest regressor, um, and then it got reduced to 22,000. Yeah. So that's um, yeah, like by 7,000. That's like, I don't know, like 30% improvement. Well, this is only like kind of like less than 10% improvement, right? Yeah. So this thing, I think it shows us like the best kind of um, random forest, right? Um, Random forest is a type of decision tree, basically. Um, so let's see, random forest, random forest. I kind of forget. My goodness, it's just been like 2 weeks and I kind of forget. So um, it's a random decision forests are an ensemble. So it's a combination, kind of like learning method for classification regression that operates by constructing a multitude of decision trees at training time and outputting the class. That is the mode of the classes. Okay. So ensemble learning method. So it consists of multiple random decision trees. The type of randomness are built into the trees. First, each tree is built on a random sample from the original data. Second, at each tree node, a subset of features are randomly selected to generate the best split. Oh, okay. So that's why the name is kind of, it says random because first it's not just one tree, one decision tree. It consists of multiple decision trees and they are random. So probably some of them is like has, I don't know, 10 leaf nodes. Some of them has 20. Some of them has 30. So you need to make it reproducible. Every time you heard the word random, make it random. Uh, y- you want to be able to reproduce it. So you have to state the random state. Um, so there are two types of randomness. First, its tree is built on random sample. First, the sample is random, and then at each tree node, a subset of features are random is selected to generate the best split. Okay, so it could be, I think this is the best split, it's the number of nodes. And then the other one is the random sample. Sorry. Okay. Cool, cool. Okay, let's go to the next. Where's the... Okay. So right now we are going to build a random forest model and train it on all X and Y. I thought we just did that. I'm not sure about this. Hmm. RT model on full data. To improve accuracy, create a new random forest model, which you will train on all training data. Um, okay. I think you just do this. Just copy this. Just copy that. Fit on full data on all the data on the training. Um, that's what I did. That's what we did here, right? I don't understand this. Why are you asking me to do this again? It's like literally it's the same thing. I don't know what's so different. Just have to this is what it is, right? On all data from the training data. Yeah, this is it. Let's see. And then read the file and apply your I don't understand this. Huh? Um, for testing. Why is it it's what's the difference? Okay, this is for training. Oh, okay. This is really for training. Okay. Wait, wait. What am I supposed to do? I'm kind of confused. So you have a training and testing. Am I supposed to do the same steps again? Okay. Okay. Basically the same steps, I think. Um, input test.csv. Okay. Read test data while using Panda. So test data is um, pd dot um, okay. CSV. Test data path. Create a test X which come from test data, but includes only the column you use for prediction. Um, okay, so so like this. Excuse me. Okay, this one, right? Create the X and Y. Wait. Hmm. Okay, I'm confused now. The list of column is stored in a variable called features. Okay. Okay, so I have to use this, I think. Yeah. Um, home data, test data, features, like that. Create a text X which comes from test data, okay, but includes only the column used for prediction. The list of columns is stored in a variable called features. Make predictions, which we will submit. Okay. Um, okay. Test prediction. Test pre test prediction. Okay, so you need to make um, the prediction of y. Okay. Um, RF model. Okay, so we already did. We're supposed to use this, right? We are supposed to use the best model, which is this guy, right? Because it has the lowest mean absolute error, right? Which is the random forest model, right? So we have to use that. It's called RF model. So we have to call that model. Okay. So so it's called RF model. Wait, RF model on full data. What's the different? Oh, yeah. Why do you have to mm, yeah, you don't have to do this. You already did it over here. Oh, this is on all training data. Oh, okay. Okay. Got it. Got it. Got it. So, okay. I got you. So it's not just train X. So you just use X basically. Got it. Okay. Okay. I got it. Okay. So you just use X. Sorry, guys. Just use X and you just use Y, right? I think that's about it. Because you're using and how do you get the X and how do you get the Y? Um, yeah, from here. Right. Wait. What am I doing? Uh, okay, I'm confused now. I think it's um okay. Should I use the full data? I guess so, right? And then you got the model here, and then you're using a new data set. It's just for testing, and you are um basically put it into like an Excel spreadsheet, into a data frame. It's called test data, and then you're putting on test X based on specific features because you just want to include specific features on that data. Um, and then you are going to predict using that model that you already trained. Um, so you are going to call um, dot predict. That's the new algorithm, right? Wait, RF model on full data? I think it should be RF model on full data. Yeah, I think that's called what is this? And then call predict, and you want to predict it on the what do you call it? The prediction is on the output, right? On the Y. So you want to produce the prediction on the test X, I think. Yeah, yeah. The lines below shows how to save prediction in format used for competition scoring. Just uncomment them. Okay, so output the spreads. Okay, I think this will do. Let's see. Let's see about this test spread. Okay, so these are the predictions. Um, I don't know what is the how do I know like what's the number? Round, set, size, shape, shape I think 1459. Okay. Okay. I think that's the one. So so I'm gonna uncomment this. So I'll put PD data frame um, test data dot ID, which is from here, right? And then the sell price is the test uh, Preds, which is 1459, which is basically an array of this. These are the prediction of the cell output based on the input of a specific features, um, based on the algorithm that are uh, being produced by after training it on the full data, um, by choosing the best algorithm, which is the um, ensemble of random forests, which is called this guy, random forest regressor. How do we know this is the best? Because it has the lowest mean absolute error, only 22,000, compared to the mean absolute error of a decision tree that has maximum leaf of 100. And this is maximum leaf of default, 29,000, right? So that's how we know what algorithm to choose, right? We have based on these three options, these are the best. So we choose that one. So we call it this guy, right? And then we train it, but this time we train it on a full data, on all data from the training data. Okay. And then after that, we use after we train it, so we have the kind of the perfect in quote algorithm. Uh, all of the hyperparameters kind of already known, like the variable, the A, the B, the C, and the features. Um, and then we want to use the tests. Why do we use the tests? Because this is like imagine this is like already you're deploying it to the real world, right? Because you already validate your data. Remember, you divided it into two, train and uh, validate. You already validated. You're happy with it. You choose the lowest mean absolute error. So you're now you got this kind of the best kind of algorithm. So you choose this best algorithm, which is called random forest regressor. You train it again using the full data. This time it's not split, it's not training and validate. This full data. So you got the model, right, with all of the parameters in place. Um, and then now you want to use this model that you got, you've just being trained on the full data on the new testing kind of data set. So the testing data set is like your imaginary, like your real data set uh, if you deploy it in the real world. So that's why you called it the test is instead of the train, right? The same thing happened. You just put it on the Panda data frame to be able to extract all of the information in the red format, kind of the Microsoft Excel format in quote. Um, you just want to get the features on the X, right? On the as a task X, right? You don't want to get all of the features. Remember, this is a machine learning algorithm, so you have the input from the domain expert. So the domain expert will tell you, okay, these are the important features. to check. So you take that into consideration. You put it into the test X, and then you call the prediction. When you call the prediction, you want to call the model that you already just being trained on the best model, kind of the optimized model on all of the data. And then you call dot predict because you want to get the output, right? And then which one do you call is the test X, right? This is the one, the input of the data that you just get from the new data set, the new testing data set based on the features from the domain expert. Um, and then this one is just to show you how do you save it, how do you output it, because this is for competition scoring, right? So you call pd.dataframe, and then the ID is the test data.id. So you're using this, and then the sale price is the which is the y. In this case, is the test prediction, right? And then you want to output it to CSV file. So you submission.csv. Okay, and then it will run this one. Let me see. Thing is, I'm not sure how this thing like it doesn't show. Yeah, I don't know. Let's just run this. Just run that. Whatever. So I'm just gonna check this. Still doesn't show anything here. Um, okay, so this is like the array. I'm just gonna close this again, and then it's gonna test your work. So this is already done. The thing is about I want to give input to Kaggle, whoever's running the Kaggle. Maybe Rachel, if you hear this, I'm not sure you want to hear my Kaggle practice, whatever, or YouTube series. But I want to be able to see like on the input here on the workspace, like the file that I'm working with and the file that I've just created. Like this one, I already created this file, like output to CSV, right? But I cannot see it here. So how do I see that? I do not know how. So if somebody can answer that, oh please, please, thank you so much. Um, so okay, so I'm assuming we already created it, right? Because we run this code already. Okay. So right now we're gonna says test your work. We're almost done here. Just bear with me. Um, oh, it's almost 1 hour already. Okay. So after filling in the code above, click the commit button. Okay. So I'm gonna click this. After your code has finished running, click the open version button. This brings you into the viewer mode for your notebook. You will need to scroll down to get back to this instruction. Click output button on the left of your screen. This will bring you to a part of the screen that looks like this. Select the button submit and you will see your score. You have now successfully submitted the competition. If you want to keep working to improve your model, select the edit button. Then you can change your model and repeat the process to submit again. There's a lot of room to improve your model and you will climb up the leaderboard as you work. There are many ways to improve. Experimenting is a great way to learn at this point. The best way to improve your model is to add features. Look at the list of columns and think about what might affect home prices. Again, you need some domain expert. If you're a realtor, there you go. Or if you have somebody your friends, your neighbor, your uncle, your mom and dad, has been in the business. Probably you might want to ask them, hey, mom, dad, whatever, uncle, or friend X, friend Y, what do you think is the most important features in determining home prices? Is it the number of bedroom? Is it the number of how many square feet do you have? Is it like it has a basement? It has a first floor? How big is the first floor? Blah blah blah, right? So some features will cause error because of issues like missing values or non-numeric data types. The intermediate machine learning microcourse will teach you how to handle this type of features. You will also learn to use XGBoost, a technique giving even better accuracy than random forest. Some other microcourses, the abundance microcourse will give you the data manipulation skills to quickly go from conceptual idea to implementation in your data science project. Okay, so we're gonna probably cover that for our next session. You are also ready for the deep learning microcourse. Ooh, deep learning. This is one I've been talking about, guys. It's amazing. Deep learning is amazing. It's the buzzword of the in today's age. So yeah. Anyway, so where you build models with better than human level performance at computer vision tasks. Have you heard about driving self-driving cars? Uh, I think it's gonna come true. I think so. I know Tesla is working really hard for that. Probably, I don't know, another 2, 3, 4, 5 years, but I think it's gonna come true. And when that things happen, poof, oh my gosh, I couldn't imagine like the implications on that on our society. Just imagine you go to your work, all you have to do is just like sit down and just do something else because everything is taken care of. You know, the car will kind of drive on its own for you. Um, anyway, so um, I need to, okay, so I need to click the commit button right now. Let's see what happens, okay? Cross my finger, committing. Okay, it still has this one. I have no idea what's doing. Oh, it's converting to IPYNB. Okay, let's just wait a second. Still running. Hopefully this is not too long. Um, I don't know. Should I return to editor? It seems like just keep on going this one. Like, how long do I have to wait for this? Writing 29,000 bytes to results.html. Converting notebook to HTML. Okay. Converting notebook to notebook. Executing notebook with kernel. TensorFlow stream. Dynamic. I have no idea what is this. Oh my gosh. Writing 10,000 bytes to notebook. Converting notebook IPYNB to HTML. Okay. Just return to editor. Oh, so it takes some time to do that. I wish like again, if this is still happening, I think it's still happening. Um, Kaggle, if you hear me now, that's another area to um, to improve. That give like a something like progress bar, like how many minutes estimate. Because right now I have no idea what's going on. Right? It's just says kernel. Oh, it's still running. Okay, but I have no idea like how long will this take. Right? Um, oh, oh my gosh, it's undefined. Why undefined? After your code has finished, and click the open version button. Click open button on the left. Shall I try it again? Kernel must be running before committing. Okay. I don't know why. Is it like, should I turn it off? Oh gosh. Let's do this again. Oh, I hate this. I hate this. Why are you doing this to me? Should I run this again? I'm just gonna run this again. Okay, I'm running this. Okay, okay, done. Just want to see the test prediction. Okay, 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 commit. Um, I think I have to just stop here. This is just a matter of committing it. You kind of try follow the instructions, and yeah, I don't know why it doesn't work. Probably, so I'm trying it again one more time. Oh, there you go. Oh, I think it's done. Um, I don't know, version 2. Okay, whatever. Um, I guess I just choose version 2, right? Um, Return to editor. Oh, wait, it's already done. Okay, so, okay. After your code has finished running, click the open version button. What is the open version button? What do you mean open version button? I don't get this. What if I do this one more time? Like, hmm, I'm still confused. Version 3, select difference. Um, I have no idea what's going on. Oh, complete. Should I go here? Okay, whatever. Okay, it's kind of confusing. I have no idea what's going on. It says click the open version button. Where is the open version button? Like, okay. Oh, this one? Huh. Wait. I'm confused. How do you? Oh, I think it's this one. Okay, okay. I think I got it. Okay, so you, if you remember for an output, you will need to scroll and to cut the left of the screen. Okay, so probably this one. Oh, here. Yeah. Okay, so you kind of like, okay, so the steps are after you, I'm just gonna close this first, kind of confusing. and my inbox. Okay, and my YouTube, just to make it okay. So after you click this, this is the first time I did this. Okay, so it's kind of like new to me. And then you come up with that window, and then you go. I think you go on the um, no, and then that window has a link, so you kind of like go to that link, just copy and paste that link, and then or you can just go to your Kaggle site. You see, right? And then you go to your express machine learning competition. Sorry, um, this one, right? Um, so it has the kind of the HTML file version of it, and then you go to the output, right? There's three commit. You can click it, or if you click it, whatever. Okay, so you just make three commit. Okay, so and then this is your output, right? So you get your output here, like 1,400 something. Yeah, 1,559. Oh no, it's still a lot. There's a lot of them. I think it's 1,400, right? Um, why the access is limited? Okay, and then what do you do? How do you submit this thing? Like that looks like this. Select the button submit, and you will see your score. You have now successfully submitted the competition. Okay. Oh, I think this is what the open version button is. The that's the link to that particular open version. We call it our website. Uh, why is it everything is like churning? How do I wait? How do I submit this? Wait, I'm confused now. How do I submit this? Oh, here. Oh, here. Okay, click that one. Ooh, yes! Finally, we did it! We did it! Okay, it's kind of stressful, but it's kind of slow. I don't know what's going on. Like, is the website slow? It's my OBS is slow. I don't know. It's kind of slow, or because okay, so we already submit our score. Jump to your position on the leaderboard. 28,800. What? Let's see. What's our position? Where? Oh my gosh. So it's 7,188. That's my leaderboard with 21,000. Um, okay, cool. Oh wow, like the first place is like almost half of it, right? It's only 11,000 to score. Cool. So that's about it, guys. Um, I just show you how to make a submitting a prediction for the housing prices competition for Kaggle. What if I press this submit prediction? Okay, it goes the same. It is my submission. You may select up to 2 submissions to be used to count towards your final. Okay, whatever. Whatever. Okay, so that's the one. And then go here. Leaderboard. I'm like ranking number 7,000 something. Um, where's mine? Um, oh, here. 7,888. Okay, cool. Whew, I'm so happy. Today's task is more than 1 hour. So I hope you learned a lot today. You're just not learning about how to make um, uh, choose the best. So just to recap, um, you want to deploy a model. First, you want to split the data into two, right? Uh, for training and for testing. And then you train it using the model that you already choose. This time we choose a decision tree algorithm model. But decision tree algorithm has many varieties, so you choose the best one. In this case, we choose like the default one with I'm not sure about the number of leaf, and we choose the number of leaf nodes. The maximum is 100, and then also we compare it with the random forest, which is basically an ensemble of a decision tree algorithm. And there are two things that are in random. One is the um, uh, I think the decision tree itself is the form is randomly selected, and the second one I think is the has to do with the data itself. I'm not sure. Okay, but there are two things are random. But basically, it's a compilation of different form of decision tree, and then you kind of like put it together as like one giant kind of decision tree. That's why it's called random forest because it's a compilation of trees, right? If you go to forest, basically there are many trees, um, and it's random because they kind of choose you kind of what the best trees. It could be a maple and a thick and uh, red bud and I don't know Korean some Korean tree or sequoias, right? Something like that. And once you determine the best kind of model that you want to capitalize on, then you choose that model. In this case, it's a random forest, and you train it again. This time using all the data. You don't split the data anymore, right? Because you already know what model is the best. The 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 reason why you split it the first time, um, because uh, first you kind of know as a quality control person, you want to know but that your model is not just good in the training world, but it's also good in the real world, so to speak, right? But once you kind of know about it, right, your world is kind of your your data is kind of sorry, your model is kind of generalized, right? So now you can and you know which model is the best among the different kind of models in the decision tree world. So you pick the best model in the decision tree. It's called random forest, and you want to incorporate all the data. Um, you train it again. You got the model, right? Based on the all the data, and then now you want to test it. You want to use that model to predict. So you call dot predict, and you use this case the testing data, not the training data, the testing data. So you got the prediction, and then you at the end you um, yeah, so that's your prediction, and you submit that prediction.